any sound is going to be characterized by the loudness. If the sound is loud, obviously you are able to hear the amplitude more. If the sound is faint, obviously the amplitude is less. So that is the difference between loudness, or loudness of a fierce sound and loudness of a small sound. Similarly, if you sound two waves having frequencies very, very close together, in that case, we say that there are production of beats. So beats are nothing but some sound waves which are produced because of very closely spaced frequencies. So those are known as beats. So let's try to understand more on this in this particular part. So now moving on, we will talk about the loudness. What exactly does loudness stand for? You would have heard multiple things. Means some things it looks good to your ears. It is soft, sober, something that is noise, right? So that is related to how much loud that sound is. Obviously, I'm not classifying that loudness is the only criteria, but it is one of the criteria based on which we try to identify whether a sound is good, whether a sound is bad. Yeah. So loudness, if you have to characterize the loudness of sound, then how do we characterize that? Yeah. So human ear is extremely sensitive to a large range of intensities, how much sound we can actually hear. So based on that, there has been a relation that has been derived which says that it is related to the logarithm of an arithmetic scale, because it covers a large range. So you cannot really plot all those values. It's better to take it on a logarithmic scale. So effectively, the loudness is related to something known as in decibels. You try to find out the factor in decibels. So loudness is given by something like 10 log to the base 10. I is the intensity divided by 10 raised to the power minus 12. So this is how we classify the loudness. And this is what the value that we classified. So this particular value is known as the original intensity. So the intensity that is given over something that is a standard value. So this tells us about the value of the loudness, and this is found out in decibels, right? Here I naught is something like a reference value or a threshold intensity that we have. Now if we move on and try to understand what all or how exactly is this loudness related. So for this, we'll try to understand about air columns. So if you have a air column, what exactly are the different types of air columns and how exactly is the frequency of sound related to it? You would have seen, or you would have even tried to blow air in a open pipe, organ pipe, that creates, if you place your fingers at different points, it produces different types of sounds, right? Have you ever wondered why does it do so? Let's try to understand it here by understanding the concept of open pipe. So what is an open pipe? Open pipe basically means it's simple to understand that it is open from both the ends. It's a cylindrical tube, it's uniform, and it's open from both the ends. So the air can enter from either of the two ends and go out. So let's say air is entering from the left, it goes out from the right, or vice versa, right? So if I say for the simplest case, let's say the air is entering from here, it goes out from here. So effectively that gives out a kind of 1/4 of a sinusoidal wave. Similarly, it can enter from here and go out from here. In a similar way, we can say that in the second harmonic, it produces this kind of a sound and goes out. Then we have the third harmonic, it produces this kind of sound and goes out. So if you talk about the first case, you see that this is not the complete one. This is not the complete wave. Yeah. So this is half of the complete wave. Since it is half of the complete wave, so we'll say that if I say the length of the tube is L, so since if I do not know what is the wavelength, so let's assume that the wavelength is lambda. So L is going to be equal to lambda over 2. In a similar way, if there are two waves, means it's a complete wave that is covered, in that case L becomes equal to lambda. It starts from here, ends up here, so one crest and one trough are completed, so L becomes lambda. And similarly, if there are three of them, so it becomes L equals to 3 lambda by 2. So this is the case of an open organ pipe. Open organ pipe, this is the first case when n is equal to 1. So there is half of a wavelength that is being covered. So this is known as the first harmonic. Then you go on to the second harmonic when the complete wave is covered. When the complete wave is covered, that is either known as second harmonic or the first overtone, and so on. Then using this you get the cases of nodes and antinodes, so which are also known as the pressure nodes. Let's take it further and try to understand it. So what do we have here? Sorry. So we have for the first harmonic or the fundamental tone, we say L is equals to lambda 1 by 2. That gives us lambda 1 is equals to twice of L. In a similar way, for the second harmonic, L becomes equals to lambda 2. So lambda 2 is equals to L. For the third case, L becomes equals to thrice of lambda 3 by 2 and so on. And since L is inversely proportional to the frequency, so you can find out how the frequencies are going to be related. So frequency of the first harmonic, second harmonic, third harmonic and so on, they're related as 1:2:3. Now, take a closed pipe, that is a closed cylinder you can say. So the best one is that the air goes in, gets reflected and comes out. So it's effectively 1/4 of the total wave that is getting reflected out of it, right? And so effectively, in a similar way, in the second case, where so 3/4 of the wave gets reflected and so on. So using this, it's always going to be an odd multiple of lambda by 4 that's going to come out of it. So for this case, if you have to find out what is the case of a fundamental node or first overtone and so on. So this is how we relate it. So the length for the first tone or first harmonic is going to be L equals to lambda 1 by 4. For the first overtone or the third harmonic, it becomes 3 lambda by 4. The second overtone or fifth harmonic, it becomes like this. So here, effectively, the frequencies are related is to 1:3:5. Now, have you ever wondered, supposing you have two frequencies which are very, very close together. So in some regions, you get some frequencies which are very, very closely occupied or very, very close together. That results into what is known as the formation of beats. So how do you get it? You can get it, let's say, if you have a tuning fork. You know what is the original frequency of the tuning fork. Now either you wax it or you further slice it or let's say vein it. In that case, the frequency with which it's going to produce the sounds is going to be slightly different, not much different. So that results into what is known as the formation of beats. Now as you know, let me try to tell you about this. So let's say I have two frequencies. One, let's say I give you y1 is equals to sine omega t, and the other one goes as y2, which is equals to sine of omega 2t, omega 1t and omega 2t. So if I just try to add them up, so what is going to be the resultant wave? Is going to be equals to sine of omega 1t plus sine of omega 2t. I'm taking the amplitudes to be same, everything else to be same. Yeah. So omega 2, if I can write down in terms of some difference, that is what I mean to say, I can say that omega 1t plus this becomes omega 1 plus delta omega into t. So as a result, if I just try adding it up, so I'll get sine omega 1t, then a plus b, if I use that particular formula, so I'll get sine omega 1t cos delta omega 1t. Then we have plus cos omega 1t sine delta omega 1t. If I have this, as a result, I can just take out sine omega 1t common. So that comes out to be 1 plus cos of delta omega 1t, and then you have cos of omega 1t sine of delta omega 1t. Yeah. So this can further be simplified, and you can write this as sine of omega 1t, and here 1 plus this can be removed, and you can simply write this as twice of cos square delta omega divided by 2 into t. And similarly, this can be written as cos of omega 1t, and this can be written as twice of sine delta omega 1 divided by 2t cos delta omega 1 divided by 2t. So this factor that you can see, of course, this results into what is known as the formation of the beats. So if we have to find it out, I have tried to relate it again. So if I say that initially I have a phase phi, and if I have another one with a phase phi 2, if I want to relate that, then you can see that there is a difference in the phase, in the frequencies that you have, in addition to the addition of frequencies. So this difference in the frequencies results into what is known as the formation of the beats. Hopefully that makes sense, right? So beats is related to the difference, very close difference of the frequencies that you have. So we have understood about the beats. So next is nothing but the beat frequency. What is beat frequency? Obviously, when they will be sounding together, there is going to be a difference in the frequencies as we just saw. The time for one beat is the time between consecutive maxima or minima. That is how we find out the beat frequencies. So first maxima, which is going to occur as we found out the relation for the cosine part. The first maxima when this value of cosine is going to be maximum, because the resulting thing is anyways a wave. So that means this particular factor is going to be 0. Then for one beat, it's going to be given by this particular relation. The frequency of beat is nothing but the difference of the frequencies, that the number of beats is equal to the difference of the frequencies. So hopefully it makes sense about what does beats stand for. So stay tuned for more. As we found that loudness can vary anywhere between 10 and 10,000. So there is a scale which is known as the logarithmic scale. So using the logarithmic scale, we try to find out the intensity of the sound wave. So that intensity of the sound wave is found in decibels. So dB is the kind of you can say unit which characterizes the loudness of sound. Now supposing you hit a kind of tuning fork on a rubber pad. So what it does, effectively it produces a kind of damping. So that changes the frequency of the tuning fork. So similar kind of situations, if you have some tuning fork which has been just sounded on a steel rod, one tuning fork has been sounded on a rubber, obviously there is going to be a slight difference in the frequencies. So those frequencies are characterized by beats as we saw here. Moving on to the last part, that is the Doppler's effects. So what does Doppler's effect stand for? Let's try to understand that in our next part.